Great, that means you haven't taken my class, so you won't have seen this material yet, but you probably know some of it. Okay, so very briefly about me, there's my background. I don't know why this is animated. I like putting pictures of the places in there. But so I did my undergrad in California, and then I stayed in California for grad school at Stanford. Stanford had a research group that's no longer there called the VLF group that really used VLF waves as a radio diagnostic for the space environment. So studying the ionosphere and magnetosphere using VLF radio waves. So it was in the electrical engineering department, but building a lot of hardware and doing radio wave processing. Then I was at BU for a while doing aurora and air glow and unrelated things. And then I came back to Stanford where they asked me to be the project manager for a CubeSat mission. And this is in 2011. Like, CubeSats were still fairly new at that point. And I didn't know how to be a project manager, but I figured it out. And that ultimately led to applying to a faculty job where they were specifically looking for someone with small satellite experience. So that's how I ended up in Boulder doing small satellites. So I've been here for 11 years now. I had 3 CubeSats that were developed over the past 5 years that all launched this spring. They're in space now. We're trying to get them all commissioned and turned on at the same time, which is very challenging with one ground station. But it's all going nicely. So there are just the places that I consider home. My research group, like I said, it's done a lot of things because my path has been all over the place. From like VLF, like I said, airglow, aurora, hardware modeling, data analysis. So we do a lot of modeling. This pointer is funny. Of various things. In that slide on the left, there's electron precipitation, there's radiation, there's meteor plasma simulations, there's VLF wave propagation. And then we build a lot of hardware. So on the right here, I've got a search coil magnetometer for VLF waves. The blue cube is an actual magnetometer, DC magnetometer. That's the very early prototype of the one that's now in space on that mission, Cosmo. And then this down here is actually an X-ray instrument. Happy to tell you more about that when there's time. That's on this mission that's looking at radiation belt precipitation via the X-rays produced in the atmosphere. So there's kind of the overview of what my group does: modeling, data, instruments, CubeSats, a lot of stuff. And these CubeSats have taken up most of the time of the past 5 years. Okay, so the lecture today, I'm going to talk about the ionosphere and thermosphere. And the instructions I were given was the ionosphere and thermosphere. So we'll talk about this a little bit. What I want to highlight here, this is an animation from NASA, obviously developed for the GDC mission, that really highlights the overall system. So we're going to talk mostly about the atmosphere and the ionosphere, the ionized part of the atmosphere, but it's all embedded in this complicated system. And towards the end of this lecture, I'll really tie back how the magnetic field and the solar wind and all that stuff, geomagnetic storms, impact all the way down to the atmosphere and ionosphere. So if you haven't seen this animation before, I love it. Because there's never been as good of an animation, simulation, of the entire magnetosphere and its response to the solar wind. So early on you saw, the very vertical looking lines are the solar wind magnetic field that's then interacting with the magnetosphere's magnetic field. You can see the bow shock and the magnetopause. All the particles in the tail there are tracking. Those are solar wind particles that have been injected and are moving back up the tail. And they'll eventually find their way, get fed in to the dipolar region of the magnetosphere and funnel down into the atmosphere in the polar regions. So it's trying to zoom in now to actually look at the atmospheric response. You can't see too much of it, but you know how the magnetic field lines tie into the polar region and really connect this whole system to our atmosphere. And that's just one of the aspects of the ionosphere-thermosphere's response to the solar wind and magnetosphere. You guys all familiar with NASA's SVS, the Scientific Visualization Studio, SVS? I could just spend hours on SVS like watching animations and videos like this, and I feel like I learn more every time I see these things. Yeah, anyway, okay. So what I'll talk about for the rest of this, and obviously feel free to interrupt me at any time with questions. I do tend to talk fast, so just like raise a hand. We'll talk a little bit about the thermosphere and the ionosphere kind of separately. And then I'll try to, at the end, kind of talk about various ways that the ionosphere and thermosphere are coupled. I'm going to do this from a fairly introductory level. So for many of you, you might see some review, but some of you probably haven't seen it before. So I always start the atmosphere with this quick derivation. And we'll do it very quickly. So if you have a volume of gas with some mass inside this volume, there's effectively three forces on it. There's the force of gravity on the entire volume, and then there's pressure from below and pressure from above. And the pressure from below and above may be slightly different, hence the dP. So on the bottom, there's a pressure P from the atmosphere below it, and on the top, it's P plus some delta pressure. And this volume has a total mass of the number density N times the mass of the particles times that column height, dH. And so this is then used to derive the density as a function of altitude, which is what we'll do really quickly. So starting from the ideal gas law, you have the pressure related to the temperature and the number density. And so the balance of forces says that the difference in pressures has to equal that gravity term, where rho is the mass density N times m. G is gravity, of course. So that force rho g dH is the same as down at the bottom. And you plug in the pressure term here to get this relationship for the mass density and take a derivative to get dP related to dH. So in the end, you end up with this very simple equation. The change in pressure, this little delta of pressure, is mg over k minus mg over kt times that delta H, the little height differential. So that's a very simple first order differential equation that we can integrate. You move the P to the other side. Sorry, the P is right. This P got moved over there, 1 over P dP. Integrate both sides, and integral of P is log of P, and solve to get this equation. So in the end, the pressure as a function of altitude is simply this exponential profile. So in the presence of gravity, which most planets have, if there's an atmosphere, it will end up with an exponential profile. And that exponential profile has this term, this capital H, which really defines the shape of the profile. So if P0 is the pressure at the surface, and then I've taken away H0 from there, then this capital H really defines that profile, right? And H is kT over mg. So hopefully this is a review for most of you. That's the scale height of the atmosphere. And there's a bunch of interesting takeaways, right? The scaled height depends on temperature, depends on gravity, and depends on the mass of the constituent species. So a hotter atmosphere tends to have a larger scale height, meaning it's more expanded, and that makes sense. Higher temperature, more pressure pushes the atmosphere away from the planet. Larger M or larger G tends to pull things back down. So if you've looked or heard about atmospheres on Mars and Jupiter and even the moon, other places like that, same set of equations holds, but you get wildly different atmosphere scale heights. Or sometimes not that different. There's a question. Compared to other planets? Like, how accurate is it? It's very accurate in the bottom part of the atmosphere. And actually, the upper atmosphere is pretty accurate, too. We'll get to that in just a second, actually. I'm not done. But, yeah, no, it's actually surprisingly very close. Yeah, maybe not surprisingly. Things like transport and winds and chemistry and other things are going to affect this, obviously. But for the most part, especially below 100 kilometers, it's a very good fit. So what does this look like? You can plot it. My pre-handwritten notes. Exponential profile on the right. And so what I'm showing again is sort of blue is a nominal profile, and then red would be with a higher or lower scale height, higher or lower temperature. If you plot it on a log scale, it's much more intuitive because it's a straight line with a slope. And that slope is, I think that's an error there. It should actually be -1/h. Gravity has a little bit of an effect, obviously, so that's going to change the scale height as you go up in altitude, so it won't be a perfectly straight line. One thing that's not always intuitive is that the scale height, yes, it defines a curve like this, but it's also kind of an instantaneous value. It's the slope of that curve at a given point. And that slope can change. So as the atmosphere temperature changes with altitude, the slope is changing, but the equations are still valid. It's not an error in the simplification, right? It's the equation's still right, it's just the temperature is changing with altitude, so you have different slopes. Okay, so how does it compare to an actual profile? So these are profiles from the MCIS model. How many of you are familiar with MCIS? Only one person? Great, excellent. That means I'm teaching you stuff that's valuable that you don't already know. So MCIS, I'll come to this a bit later. MCIS is kind of the go-to model for Earth's atmosphere from the ground to 1,000 kilometers or so. It stands, I'll come back to it. It stands for, what does it stand for again? An incoherent scatter. Mass spectrometer and incoherent scatter. It's a very intuitive name for an atmosphere model. It's because those are the methods by which the data is acquired. So here's a model profile of the atmosphere, and I've drawn on it because I plotted it on a log scale, just like on the last slide. And you can see there's a very good flat straight line there below 100 kilometers. And so that scale height in what's the lower part of the atmosphere is about 8 kilometers. That's the step in altitude where the density drops by 1/e, right? And then it takes a knee here at a little over 100 kilometers, and now it's got a different slope, and it's curved a little bit in the 3 different model runs here, but it's relatively straight. So the scale height model, this exponential model, is actually still valid, but what's happened at the higher altitudes is the atmosphere's temperature and composition have changed significantly. It's a much higher temperature, and it's a much lower constituent mass, as I'll get to in a second. All right. So that sort of ties to the next slide here, looking at composition. So what I've done is I've broken up the composition into these main constituents here, and then the solid black line is the total, which is the same as the previous slide. So down at the bottom part of the atmosphere, what we call the homosphere, it is pretty uniformly N2, O2, and argon. The things you know very well, 78%, 21%, and roughly 1% argon. And those percentages hold up to almost 100 kilometers. At that point, the atmosphere changes, and we start to see those 3 kind of exponentially continue to disappear, but now you see a big increase in atomic oxygen in particular, so the red dashed line right here shows up. And that's because solar ionization is separating O2 and creating atomic oxygen. Solar radiation, excuse me. And then you're also seeing helium start to increase and hydrogen, and there's atomic nitrogen and stuff as well. So in this part of the atmosphere here, kind of 100-ish to 400 or 500 kilometers, the dominant species is actually that atomic oxygen, O. That is the #1 species. There's parts of the atmosphere where it's 90% of the atmosphere. That also happens to be altitudes where we fly a lot of satellites. So they're actually flying through an atomic oxygen atmosphere. Over here, I've just done it as fractional composition, so you can really see there that this is 1 and this is a very small fraction. I should really replot this, but that's the dominant species. And then at higher altitudes, the green line takes over, that's helium. So helium becomes dominant at even higher altitudes. And if we went up even higher, there's a point where hydrogen becomes the dominant species. And so this upper atmosphere is called the heterosphere, where the composition is changing. And essentially what you're getting is the separation of these molecules, and each of them has their own unique scale height. Atomic oxygen has a scale height depending on its mass. Helium has a scale height, and you can kind of see the slopes here, right? Oh, this pointer is a little funny, right? Atomic oxygen's got its own slope depending on its M. Helium has a different slope. Hydrogen has a much steeper slope because that KT over mg, they just have different m's. So they're kind of unique atmospheres sitting on top of each other with their different scale heights. You had a question?
Do you also get neutrals above the exobase?
Above?
Above the exobase, say above 300 or 400 kilometers.
Do you have neutrals? This is all neutrals.
No, do you get, or usually they get ionized above the exobase?
They do get ionized, yes. We'll come to the ionized part of the atmosphere shortly. Yes. But yeah, these are all the neutrals. I'll talk about the ions.
It's not fully ionized.
It is not fully ionized. It is, I'll come to that. You'll see, I have a plot. It's very partially ionized. Does that answer your question? Yeah, okay. All right, so there's composition. Temperature, KT over mg, the temperature is a key part. So the previous slide talked about the homosphere and heterosphere. That's based on composition. You've all heard these terms before, I'm sure. Troposphere, stratosphere, mesosphere, thermosphere. These are the separations of the atmosphere layers by temperature. So the troposphere, the temperature decreases kind of linearly from the surface up to about 15 kilometers. And I'll come to sources of heat in a second, actually. And then the top of the troposphere is the tropopause, where the temperature turns over. And you've got this hot region in the stratosphere. And the hottest point in that middle atmosphere is the stratopause. And then it cools down again in the mesosphere. And then increases again in the thermosphere. There's two major things happening. Number one, in the troposphere, actually there's three, but I'll start with the first two. In the troposphere, it's warmest at the surface and it gets cooler as you move away from the planet. That's because the surface absorbs most of the sun's heat, visible light, heats the surface, and then the Earth itself becomes a radiator. It's radiating infrared back towards space, and it is absorbed in the atmosphere as it is radiated away. So as you get further away from the planet, there's less atmosphere to absorb that heat. So it gets cooler as you go up in altitude. At the top of the atmosphere, all of this heat, this high temperature, is due to absorption of solar ultraviolet radiation. So the thermosphere is where most of the ultraviolet is absorbed, and it heats that part of the atmosphere. So naturally, you have a hot part and a hot part at the bottom and a cooler part in the middle. And so most atmospheres actually have that simpler shape. But the bulge in the middle is due to ozone. The ozone absorbs a lot of specific wavelengths of solar ultraviolet light and heats that part of the atmosphere. So this is the cartoon version, and then on the right, again, is from the MSIS model that also produces temperature for us. And I'm showing you a couple of different profiles. And the reason I chose those particular dates is day versus night, but also solar cycle differences. So 2016 is around solar minimum. 2009, I think, is around solar maximum, if I've got that correct. But ultimately, the day-night difference is pretty large. You can see the thermosphere temperature can change from 500 to 1500 kelvins, whereas the lower part of the atmosphere doesn't change nearly as much. Little differences. Okay? Yeah. Use the box.
The pauses on the doodle have specific heights. Do they move significantly, and are they very thick or thin?
Yeah, I mean, the pause is really just a change in the temperature, change in the gradient of the temperature, right? And you can see that here. The mesopause has moved down in this red curve. So they do change, yes. By a few kilometers, maybe 10 kilometers even, depending on various conditions. Thank you. But you know, these are pretty good nominal estimates of those altitudes. Yep. It's supposed to be throwable. Designed to be thrown.
Thank you.
No one wants to throw it.
So just to work off of that question, this assumes that this is like daytime, right? Like because as thermosphere temperature is kind of going up, this is half the part of the Earth that is
In
being
daylight,
bombarded
yes.
by solar radiation. But
Yeah.
what about the other part? Is
On the night side,
yeah, on the night side is something similar.
the night side is going to actually look very similar, and we'll talk about that here in a second. So what I've mentioned so far are the sources of heat, right? The balance that gives you a sort of equilibrium temperature, there has to be cooling as well. And so we'll talk about cooling in a second. But essentially what happens, obviously, the day side is when it gets heated. It moves, the Earth rotates, the atmosphere is on the night side. It just doesn't cool that quickly. So the profile looks pretty similar. There is going to be some cooling, but it's not, the thermosphere doesn't disappear by any means.
Oh, I see.
Yeah.
But there's nothing for O2, like the O2 is, ozone is absorbing UV radiation, right? But
Yep.
when it's to the night side, it's still not absorbing, but it just keeps that temperature profile or something like that.
Yeah, consider it's basically absorbed a bunch of heat. It's got trapped heat, and that keeps the atmosphere warm. There's various processes by which it can lose heat, but just like taking something out of the oven, right? It's going to lose heat, but not instantaneously. If you put it back in the oven before it's cooled down, then it's going to kind of look the same. All right. So actually, kind of addressing some of these questions. This is kind of an interesting plot that I like. I forgot to put the citation on there. Don't learn from me. This is from Dolores Knipp's book on space weather. And what we're looking at is the temperature during solar maximum, during the March equinox, so the sun is directly over the equator at noon, at 8 different altitudes. So starting from the surface, so this label goes with that plot, and then the tropopause, and then the stratopause, and the mesopause, and then different altitudes within the thermosphere. So at the surface, get this pointer to behave, you'll notice, as you can expect, the surface is hotter at lower latitudes. The sun is more directly overhead. The poles are cooler. So there's 300 kelvins and about 250 at the poles. When you go to the tropopause, up to that 15 or 16 kilometers, it flips. And the tropopause is actually cooler at the equator and warmer at high latitudes. I'm not going to get into why that is. It flips again at the stratopause, where it's warmer at the equator and cooler at the poles. But they're each still following the same trend, right? Hottest at the surface, cold at the tropopause, warmer at the stratopause, very cold at the mesopause. And same thing for the poles. It's getting colder, getting warmer, getting colder. It's just the shape of those curves is different for latitude. Now at the mesopause, things are getting a little bit weird. It's no longer got this very simple latitude structure, because now the rotation of the planet and day versus night is making more of a difference. So you get into the thermosphere, and now you see most of the heat is basically directly below the sun. And there's less of a latitude dependence. So you get this structure now within the thermosphere where the atmosphere is quite a bit warmer on the day side. So it's back to this day-night question, right? Day side is warmer, but on the night side over here, it's a few hundred degrees cooler. But it is still pretty warm. 896 kelvins. And that hotspot is also, it turns out, about a couple of hours east of the subsolar point, the warmest part of the atmosphere. Essentially, there's kind of a time delay in the heating of the atmosphere. There's a lot of structure. Okay, so this is also from Dolores Knipp's book. This is where that plot came from on the top. And this is, I like this, it's a lot of text. But if you spend a little time reading it, it does a very nice summary of the sources and sinks, the sources of heat and the sinks, which means the cooling mechanisms. So as I said, the troposphere is mostly absorption of solar, visible, and infrared, although there's some other sources as well. And then most of the loss of that heat is due to infrared radiation. So the surface of Earth is at roughly 300 kelvins. It's a black body, and it's radiating at the 10 micron peak wavelength, right? Black body radiation. It goes this way. So in the stratosphere, again, the source is strong absorption of ultraviolet by ozone. And then the sink, the loss of that heat is through, again, through infrared radiation. Mesosphere, there's some, you know, ozone absorption, kind of the bottom of the mesosphere, which is really part of the ozone bump. Transport of heat down from the thermosphere, just at the very top of the mesosphere, and then chemical stuff that we'll talk about. And again, infrared radiation. Different constituents are kind of the predominant radiators in different altitude regions. Thermosphere, this is where most of the extreme ultraviolet from the sun is absorbed. There's also, some of the energy goes into ionization, which we'll come back to, dissociation of particles, all sorts of other stuff too, Joule heating because of the aurora, particle precipitation adds a fair amount of heat. And then there's heat that's actually transferred from below up into the thermosphere by gravity waves and tides and planetary waves that I'll talk about a little bit. And then again, there is some energy heat transfer downwards into the mesosphere, but mostly it's again infrared radiation. So all this atmosphere is sort of in balance due to it's got some temperature, it's a gas, it's going to radiate infrared. Right? Okay. One of the interesting features, of course, of the upper atmosphere is air glow. This is not the same as the aurora, but it's really handy. These altitudes, sort of from 100 kilometers to a few hundred kilometers, the mesosphere and thermosphere, as I mentioned earlier, are largely atomic oxygen, so certainly in the upper part. There's also OH, there's also O2, a little bit of N2, etc. There's a sodium layer that I didn't talk about before. And these parts of the atmosphere also, they actually glow. So they will get hit by solar radiation, which will excite the atoms, which will then emit visible light. And so during the daytime and nighttime, it's easier to see at nighttime, obviously, the atmosphere glows. The yellow in here is primarily the sodium line. The green at around 100-ish kilometers is an oxygen line at 5577 angstroms, 557.7 nanometers. And this red up here at around 200 or 300 kilometers is also atomic oxygen. So atomic oxygen is just glowing, emitting light constantly. And it's a very handy tool because we use this to study this part of the atmosphere and ionosphere. It's the easiest way to actually see the environment. And so I'm going to talk about that a little bit later with some of the missions. Yeah, I could go into much more detail on these emission lines, but we won't do that right now. There is a little bit of a layer around 100 kilometers as well that you can't really see, which is all these OH band emissions. And they're commonly used to study that region as well. Yeah. Question, sorry.
Oh, okay, sorry.
Stretching. So, again, this is actually not from NASA. Oh, good, the audio is not working. There's some weird, funky music that goes with this. But this is from the ISS, and this air glow is actually visible from, most cameras, but sometimes from the naked eye. And it's just really cool. There's also lightning happening. So you saw the red air glow layer that disappeared. It's coming back again. They're going to be more prominent actually in sunlight, but they're much easier to observe at night. And I want to show you something that comes up here in a little bit, which is there. So you see in the red, there's some structure. It's not just a flat band. And in your mind's eye, if you can kind of draw slanty lines like this, the air glow is actually following Earth's magnetic field. So there's some striations and structure in there that are largely driven by the magnetic field. And now the animation's doing why? I don't care. Astronomy. We're not here for astronomy. I'm going to zoom back out again. There you go. So I'll come back to this a little bit, as I said, when I talk about how we use this to study the environment. All right, so I gave you a kind of a blanket picture of the atmosphere. Obviously, it's not static. There's a lot of variation from day to night, but there's also a lot of variation with the solar cycle. And the solar cycle variation, there's really not huge variation in solar visible output. The total power output from the sun, which is dominated by the visible spectrum, 1,366 watts per square meter at 1 AU. That doesn't really change. But the amount of stuff in the EUV, in the ultraviolet, changes dramatically by orders of magnitude. And that's responsible for most of the thermospheric heating. So down here is a plot of temperatures for solar maximum and solar minimum, laser pointer. And so again, you can see there's that huge factor of 3 difference in the temperature of the thermosphere. I'll get to the neutral density and electron density. Well, I'll get to the electron density later. The neutral density you'll see is also changing, and this is the scale for the neutral density. So that's 1 to 2 orders of magnitude difference in this upper atmospheric part, the thermosphere. This is data that is measurements of that density, nanograms per meter cubed. It's not a huge density, right? Over the course of multiple decades. And so here's that solar cycle variation, and it's about an order of magnitude in density. And notice that the data is labeled as satellite drag data. So it's actually measured by looking at the drag on a spacecraft and using that to back out the atmospheric density. Which also tells you, one of the things that's important for this upper atmosphere is its effect on satellites through drag. If we can't predict the atmosphere very well, then drag on spacecraft is also not very well predictable. And that leads to a huge uncertainty in the position of spacecraft and increased probability of collisions. Well, probability of not knowing if there's going to be a collision, put it that way. So I'm in an aerospace department, and that's one of our huge topics. We study the atmosphere largely so we can better predict the atmosphere, so we can better predict spacecraft trajectories. And this is actually, so there's a plot over multiple decades, and then here they're kind of stacked with years since solar minimum. And so you're seeing the solar cycle variation, that's the larger trend, and you're also seeing kind of a diurnal variation, not diurnal, seasonal variation in that density as well. Right? The composition will also change, and a lot of this is coming from the basic principle that I just told you at the beginning. It's the scale height of the atmosphere. So more heat, more ultraviolet from the sun means more heating. More heating means higher temperature, and through KT over mg, that increases the scale height. So the whole atmosphere expands and sort of stretches upwards. And so all of these profiles, here's solar minimum, and here's solar maximum. Again, the ones on the bottom are the fractional compositions. These are the actual compositions. And so if you look carefully, you'll notice like the red line for atomic oxygen, they're on the same scale on the x-axis. The red line just sort of tilted upwards to have quite a higher slope. And that stretched the region. Over here, the region where atomic oxygen was dominant was only up to about 400 kilometers. And then helium takes over. Now atomic oxygen is dominant up to 800 or 900 kilometers, just because the slope of that profile changed dramatically. All right? So the composition is changing, but largely because, especially in the thermosphere, because all of these profile slopes are changing. All right. So actually, if I go back a second, in this region, you do still have, so the blue line is N2, our dominant species down here at the surface, and it's still one of the major species up in this altitude range. Of course, it's less over here in the solar minimum. O and N2 together are often used as a pair to sort of measure the effect of the atmosphere. So this O to N2 ratio is a really common measurement. And so it's measured by different optical emissions or other methods as well. And so this instrument is using the column density by integrating downwards, the column density of O and N2, and using that ratio to see variations in the atmosphere. So it's a proxy for the neutral composition and heating of the atmosphere, and provides really interesting insight in structures throughout the atmosphere. So this is 6 consecutive days in 2004 around the time of a geomagnetic storm. So you see a big enhancement in the atomic oxygen density here, so increase in the O to N2 ratio. I don't know why it dips on the 9th and then comes back on the 10th, but there you go. There's a lot of interesting structure that can be seen that way. All right. Okay, so I'll pivot to kind of some other phenomena. So I was kind of looking at a static atmosphere, right? Just composition, balance of forces, nothing moving. But in fact, the atmosphere is constantly in motion. I'll just give you some highlights because this is not really my area of expertise. But here's an example where using an instrument on the TIME spacecraft, we're looking at winds. And whoops, go back. And so the winds here in this plot, they're derived again from observations of that red air glow line, that 630 nanometer line, the red emissions in the F region, or it's not the F region, in the thermosphere. Getting ahead of myself. And because they're line of sight, there's kind of a range of altitudes that it spans because it's an instrument that's sort of cutting through a range of altitudes. And so from that, you actually look at the Doppler shift of that 630 nanometer line, and that gives you a velocity of the atmosphere itself, moving towards you or moving away from you. You get a little Doppler shift in those optical emissions. And so from those, you can derive these wind vectors. And so notice these wind vectors, the little scale down there, there's a little black arrow, is 200 meters per second. So wind speeds can be tens to hundreds of meters per second up at these altitudes. So the atmosphere is moving pretty quickly. This equation kind of summarizes the motion of the gas based on these forces that I have listed here. So you're looking at horizontal winds in particular, and they're driven by a pressure gradient. So obviously if I have a high pressure region and a low pressure region, there's going to be motion of the atmosphere by diffusion. The Coriolis force due to the Earth's rotation, viscosity of the atmosphere, with this viscosity mu, and ion drag, where we'll come to this when we talk a little bit more about the ionosphere. But the neutrals are moving through all these other forces. They collide with ions. The ions have their own forces on them as well. And the two are coupled through collisions. So they'll tend to drag each other one way or the other. And so this sort of ultimately affects that overall wind speed. So different parts of the atmosphere, these different terms are going to dominate, but all of this is going to give us a fairly complicated horizontal wind profile for this atmosphere. And I'll show you some more examples of that later on. The terms in here, everything's fairly intuitive. That's pressure. Sorry, that's density. That's pressure. Nu Ni is the collision frequency between neutrals and ions. Capital U and capital V are often used interchangeably for the actual velocity, right? So this UH is the horizontal velocity of winds, and V is the ion velocity. All right? And then we also have tides, and tides, again, are sort of periodic motions within the atmosphere, whereas winds are kind of, I don't want to say micro scale, but think of them as regional effects. Tides and planetary waves are sort of global phenomena. They're going to be periodic around the Earth, whether it's a tide that's sort of like a first mode with the moon, for example, or they can have higher order tides due to different phenomena. So this is an animation that I grabbed from Jeff Forbes that is just showing one of the complex modes within the atmospheric tide phenomenon. And it's actually showing changes in temperature and color. And then the little arrows, the reference is 50 meters per second in this case, and that's at 100 kilometer altitude. So you can kind of see this periodic beating effect of the atmosphere. So those tides are going to be driven by, again, they're periodic, so they're generally driven by periodic inputs. So that's heating from the sun, and there's the day-night cycle. That's very periodic. So there's a tide associated with the sun's heating. The moon has an effect, obviously. It pulls on the atmosphere. You can also get interactions between tides and planetary waves, such as these guys. And you can have waves and tides driven from below by things like thunderstorms, even earthquakes, tsunamis, etc. Sort of drive perturbations of the atmosphere up into higher altitudes and will trigger these periodic responses. Tides can be sun-synchronous, or they can be non-sun-synchronous, non-migrating tides. And an interesting effect with both these waves and tides, the density of the atmosphere falls with altitude, right? This exponential profile. That means that the amplitude of these fluid waves increases with altitude. which is partly why you're getting these very high wind velocities. The amplitude of those waves and tides can be very, very large. Okay. So I'm almost through the atmosphere part here. I think this is my last slide on atmospheres. I wanted to highlight the models. So again, I introduced EMSIS earlier. EMSIS is really the go-to model that all science community uses. Back when I was a student, it was the EMSIS E90. And now NRL EMSIS E00 is kind of the standard. Everyone still just calls it EMSIS. The NRL is because it was developed by the Naval Research Lab. All of these, both of these, are empirical models that give you density, composition, and temperature. They're named as such because the data comes from mass spectrometers, incoherent scatter radars, but also rocket measurements, optical measurements. And the model can be run for different solar activity, for different locations, etc. They are empirical, but they're all sort of averaged models. They're never going to give you a perfect instantaneous snapshot. They're going to give you sort of an average, most likely atmosphere under those conditions at that location. But they're pretty good. So EMSIS is commonly used, but there are numerous other models. This is the US standard atmosphere. It's really ugly. If you get to any of these links, or if you just Google CCMC EMSIS, that's probably all you need to put in. It'll take you straight to their webpage. You can run it on the web. You can get profiles. You can download them. You can play around with them. You could do it right now. It'll take 3 minutes. They're very handy. Question? What altitudes? They go from the surface to, I believe, 1,000 kilometers is the top. I don't think they go beyond 1,000. I don't know that they do. I've never personally looked at that. Does it to go above 1,000? Yeah. Oh, does it? Yeah, as you go to higher altitudes, I don't know if you guys know better. I think now you're really getting into the exosphere and even to the corona, where measurements are much more limited. Yeah, but I believe these are entirely empirical, so they're not using physics to, unless they've added something that's using physics to extrapolate to higher altitudes. Interesting. Okay, cool. So let's move on to, unless there's any other questions, to the ions. So I repeat the same slide I showed you before in order to highlight over here, major energy source in the thermosphere is the photoionization of O and O2 and N2. So here is on the left the sun's spectrum, although this is not my favorite plot, I have a better one coming up. It gives you the total irradiance as a function of wavelength, so from 250-ish to 2,000 nanometers. There's the visible part, all that's ultraviolet, all that's infrared. This part here is what reaches the surface, the bottom plot. The yellow is the perfect black body curve. The orange is the actual spectrum. And then at the top of the atmosphere. So some of that has been absorbed actually through the sun's atmosphere. And then the bottom part is what reaches the surface. So there's a lot of like absorption cutouts here, here, and here that are mostly actually absorption by water and CO2 in Earth's atmosphere. But here's what you get at the top of the atmosphere. So if you got solar radiation and you've got constituents like N2, O2, and atomic oxygen, they're going to get ionized. So I get asked sometimes, does such and such a planet have an ionosphere? If it has a star and it has an atmosphere, then yes, it has an ionosphere. Can't avoid it. So how does stuff get ionized? This is really the really basic stuff, but it really applied to our atmosphere. So here's my better plot of the solar spectrum. On a log scale, both in power density and in wavelength, Are you guys all familiar with angstroms? Who's not familiar with angstroms? Don't be shy. I'll just tell you. Angstroms are, 1 angstrom is 1/10 of a nanometer, 10 to the minus 10 meters. It's a useful unit for optical, just because we're in the sort of hundreds of nanometers, hundreds of angstroms to thousands of angstroms range. All right, so here's the visible spectrum starting at around 100 nanometers up to, is that 1 micron? Yeah, that would be 1 micron. So the visible, the near ultraviolet, and then of course the infrared. And then we're really highlighting here all the extreme ultraviolet, soft X-rays, etc. So this is the ionizing stuff. And as I said, the visible spectrum with solar activity doesn't really change very much, but this hair on the left, the ultraviolet, will go up and down like crazy. Now, over here on the left is an example ionization cross-section, or actually it's all the different cross-sections for N2, for nitrogen. So given an electron or a photon interacting with N2, colliding with N2, based on the energy of that colliding particle, cross-sections are basically the probability of something happening, right? And so there's a probability of excitation, which means you're exciting the atom where it will then emit light, or dissociation from N2 into 2 atomic nitrogen, or ionization in red. So there's a probability that peaks somewhere here in the tens of eV and then actually falls off with higher energies. And there's also a threshold of around 15.6 electron volts. So that's the minimum energy needed to ionize nitrogen. And here's the minimum energies needed to ionize all the stuff in our atmosphere: N2, O2, argon, atomic oxygen, helium, and hydrogen. With the exception of helium, they're kind of all in that 13 to 16 eV range. And that means that the minimum photon you need to ionize is all in this 80 to 100 nanometer range. So that is telling us, and then helium needs more energy because it's very comfortable. It likes its 2 electrons. That means that, oh my gosh, the pointer. This is really our minimum ionizing wavelength. And everything below there will ionize the atmosphere. Okay? My brief lecture on ionization. Okay, so our ionosphere is ionized by all of these things. I like this plot because it's showing relatively quasi-quantitatively where these different wavelengths are absorbed in the atmosphere. So visible and infrared makes it to the ground. Near ultraviolet kind of makes it to the ground. Middle ultraviolet, those are the ones you want sunscreen for. And then the FUV and EUV and X-rays are absorbed here in these higher altitudes of the atmosphere. And then the ultimate result is that they will produce ions and electrons, mostly positive ions, negative electrons, with this profile. And I'll talk about how this is produced in a second, but the quick breakdown, you've got a peak in the ionization that's called the F region, up at around 300 kilometers, and that can vary from 220 to 350 or 400 kilometers, the actual peak altitude. Sometimes the F layer is split into F1 and F2. And then down here at 100-ish kilometers is what's called the E layer or E region. And then below the E region, there's a D region. And most of my research actually is focused on the D region. And so you'll notice it's not a simple profile. It's a slightly complicated profile. And it has to do with the different compositions of the atmosphere, whether it's O2 or N2 or atomic oxygen, or the chemical byproducts of those atoms that are being ionized, as well as the whole spectrum of the sun's radiation. All of these wavelengths, and even if we get to more granularity, they're getting absorbed at different altitudes. And so that produces this very structured ionosphere. You'll also notice, of course, that there's a huge difference between solar maximum and solar minimum. So dashed are solar min and solid are solar max, and then day versus night as well. And that should be no surprise. It's really just a change in the solar irradiance hitting the atmosphere. Okay? So I already labeled this one. This actually comes from a different model that I'll mention called the International Reference Ionosphere Model. It's a better acronym, the IRI model. And IRI is the MSIS equivalent for the ionosphere. And once again, you can go onto CCMC, IRI, and just plot profiles. It gives me some, don't ask me about these weird knees that are here. That's obviously not physical. That's an output of the model. But what I've done here actually is plot the neutrals and the ions on top of each other. So I took MSIS neutrals and IRI ions and put them on top of each other. Black line is the total neutral density, and then here's our normal main constituents of the neutral atmosphere, the atomic oxygen dashed red, the N2, the O2. That's going to be helium and green, and so on. And then I've also plotted ion densities in the sort of thinner lines. I apologize, they're not as thin as they should be. But this thinner black line over here is the total electron density. Well, it's the electron density. The electron density equals the total ion density. You might have a whole bunch of different ions, but the total number of ions adds up to the number of electrons. The dominant ion for most of the ionosphere is O+, because the dominant neutral is atomic oxygen. So atomic oxygen gets directly ionized by solar radiation. You have a lot of O+. But we do have a decent amount, especially down in the E region, of these two, O2+, ionization of O2, and NO+, and then a little bit of N+, ionization of the dissociated nitrogen, H+, which is just protons, and a little bit of ionized helium down here with this weird numerically problematic curve. So there's kind of the main ions, right? And I'll come back to this. You're probably wondering why this is not just N2+, and I'll tell you in a second. But I also want to highlight the thing Nick Gross mentioned just a second ago, which is even at these high altitudes at 600 kilometers, the difference between the neutral density here and the electron density is still an order of magnitude or more. So even at those altitudes, it's still weakly ionized. Less than 10% of the atmosphere is ionized. So when folks are saying they're doing research in the ionosphere, they're studying the ionized part of the upper atmosphere, but they're still surrounded by neutrals, mostly atomic oxygen. Okay, I'll do a really quick, of my watch on, do a really quick derivation of how the ionosphere is produced, and that'll kind of get us to these profiles and the chemistry and all that stuff. So I go through this in more detail in the class that I teach, but the very basic principle, of course, is that you've got ionization, you have some intensity of sunlight, capital I, and as the sunlight propagates into the atmosphere, it gets absorbed progressively, and so there's a loss of intensity, dI, which depends on the intensity itself, the number density of absorbers, some absorption cross-section, and a little differential height. And the differential height along the path of the sunlight can be related to actual altitude using the solar zenith angle here, chi. So that converts dH into dz secant chi. So here's again a really simple first order differential equation, which I can solve to get the intensity as a function of altitude, which is the intensity at the top of the atmosphere, I infinity, and this exponential curve, which has an integral in it with neutral density and other components. So it's a little bit of a mess. If the neutral density profile is our simple exponential from the atmosphere, then I can plug that in, and now I can actually integrate this thing, and we get this relationship, that the intensity is I infinity times this exponential, which depends on the number density and the scale height, capital H. So scale height is going to make a difference, obviously, because the higher the scale height, the less penetration that sunlight's going to get. So writing this out, you get an equation like this, which again is kind of gross. There's still an integral into the exponential. And now I've expanded it too. This simplified version was for one species. And if instead I have many species of absorbers, then like N2 and O2 and atomic oxygen, now I have to sum over all those species. And technically this is also incorrect because we're going to have, everything's going to be a function of wavelength, and we have to integrate over wavelength as well. But we won't worry about that right now. So this is called the optical depth of the atmosphere, this e to the minus tau of something. That tau is an optical depth. And so it's a measure of how quickly the intensity decays with altitude. So this kind of leading into this discussion of how do we actually get ionization production? Well, I've got some intensity, which I just showed you on the last slide, is changing with altitude. And that intensity times the number of constituents times the ionization cross-section gives me the ionization production rate. How many ions are produced per meter cubed per second? And this ionization cross-section is sort of broken into two parts here, where there's an overall cross-section, sort of how much light gets absorbed, and an ionization efficiency. What's the probability during some absorption event that we'll get ionization versus dissociation or excitation, or nothing? So in the end, that's an ionization cross-section, which again is in centimeters squared. So we can solve this equation. We can plug in the I from the previous slide to get this mess, and then write it all out to get this mess. And now I've got, there's an intensity, a cross-section, ionization efficiency. Here's my atmospheric density profile, N0 e to the minus z over h. And then an e to the minus stuff with an e to the minus c over h, an exponential of an exponential. It's really gross. So we're going to definitely just plot this rather than trying to make sense of it. So here we go. All right, so here is the profiles of that I. This is the intensity, which starts at I infinity, so I've normalized it to 1. And as I go deeper into the atmosphere, the intensity disappears as the sunlight is getting absorbed. I'm looking at ultraviolet. And it's a function, here I'm just plotting it for different solar zenith angles. So at 0 solar zenith angle, that means the sun is directly overhead. That's my maximum curve and also lowest in the atmosphere. It's got less atmosphere to penetrate than sunlight coming in at an angle. And then I go all the way to 75 degrees. You don't see a huge difference. And then right near the horizon, the profile is shifted up considerably in altitude. And that's going to be responsible for moving the ionosphere up in altitude. So if I take this and I plug that in for my production rate equation, here's what I get. And I get this curve here, which obviously has a peak. And so there's the peak altitude where ionization production is going to happen. Obviously, it's lowest and most production for solar zenith angle of 0. The sun is directly overhead. Versus near the horizon where there's just this tiny curve you can barely see, and the profile is all the way up here at above 200 kilometers. So this is just on a linear scale, and then the same thing on a log scale. You can see that effect a little more clearly of the ionization peak is reducing and the altitude is going up. And from those equations, the really ugly equations on the previous slide, you can actually get a couple of useful terms. What is the altitude of the peak of ionization? And it's this relatively simple relationship that is a function of the scale height, the solar zenith angle, and the peak atmospheric density, N0. And what is the maximum ionization rate at that peak? And again, relates to the total intensity, the scale height, solar zenith angle, ionization efficiency, and an e to the minus 1. So those are really handy terms there, the P max and Z max. Okay, so there's the basics of production. But production is only half the story. We can create ionization, but that's not the electron density profile. That's just the production rate. The production rate has to be balanced by some loss of ionization as well. And primarily that's recombination. So the ionosphere is going to be in equilibrium when production and loss are balanced. The really simple equation for the electron density is this first order differential equation. This is actually just the continuity equation, where dN dt, the change in electron density, is production minus loss. So if I had no loss, the electron density would just increase forever, and that doesn't make any sense. So there's got to be some balance where this is going to be equal to 0, so production and loss are balanced. Now, in a simple ionosphere, and this is what's called the Chapman model, the loss term is proportional to the electron density squared. So if I have a simple ionosphere, like up in the F region, where it's mostly atomic oxygen, production is just ionization of atomic oxygen. O gets hit with a photon, you get O plus and electron. The loss is just recombination. O plus finds an electron, and through some recombination rate, alpha, it recombines to make neutral atomic oxygen again and releases a photon, infrared probably. So when those are balanced, if I have a simple ionosphere with just this one constituent, then the number density of O plus and the number density of electrons are the same. And so this loss term is just alpha Ne squared. So just plugging that in for L, there is my electron density. Easy. So the P is the gross equation from 2 slides ago. And alpha is just the recombination rate from this reaction. And now I've got an electron density profile. So to complete the picture, here's the same I curves as before. Here's the same production rate curves. Now I plug it in, and here's my electron density profile. So I've got a peak in electron density somewhere here. This is a totally made-up example, by the way. Don't believe all the numbers, because I just made it up. And again, with solar zenith angle, it is reducing in electron density and decaying to higher altitudes and spreading out a little bit as well. So here is the equation for that electron density. And it can be written, it's written now in terms of P max and Z max. And this Z1 is actually the distance from Z relative to Z max. 510 minutes. 50 minutes. So I'm like halfway. I got a lot of time. I've never actually finished a lecture on time in my life. This might be the day, depending on questions. So this Z1 is just, it's measuring the distance from the peak in units of scale height. And that's just convenient to put it into this equation. So we actually end up with a not too complicated equation, except for it still has an exponential of an exponential. But that's the equation for the Chapman electron density profile. Simplified ionosphere. It's simplified because we assumed one species, and we kind of implicitly assumed one wavelength because of only having one cross-section. So it's obviously going to be more complicated. So why do we get all these different layers? It comes from the absorption of different wavelengths at different altitudes by different species. The I of Z depends on wavelength. Depends on the wavelength-dependent absorption for each species. So each species has a cross-section that's a function of wavelength. And that's what I just said right there. And so this is a really nice plot that actually shows you for all of these ionizing wavelengths. And remember, it's kind of 0 to 100 nanometers is really the ionizing sources. This shows you, this is effectively that I of Z normalized. The intensity decay through the atmosphere. So red is 1. It's 100% of that sunlight. And then as we go down in altitude at any given wavelength, it's going down by e to the minus, there's 3 lines here, e to the minus 0.5, e to the minus 1, so that's 1 scale height-ish, e to the minus 1.5, and it's gone, right? So this really highlights how different wavelengths really reach different altitudes and are absorbed at different altitudes, giving us a lot of structure. Okay. All right, so in the different layers, the simplified chemistry, yes, Nick, you have a question?
What I said was 15, 1.5.
Oh, I thought you said 5-0.
No.
Okay, I will keep my record alive. Because I do have a lot more slides. Okay, I'll try to get to the really more interesting stuff quickly. So with these different constituents in the atmosphere, atomic oxygen, N2 and O2, there's different chemistry. The stuff back here, this is chemistry. Very, 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 very basic chemistry. Chemistry gets more complicated with our multiple constituents. So we have ionization of O plus, O2 plus, and N2 plus, like so. Sorry, ionization of these guys producing those guys. But then they interact with each other to do charge transfer reactions. O2 collides with O+, it creates O2+ and atomic oxygen again, and so on. And this reaction in particular is pretty interesting. N2+ collides with atomic oxygen and is a very fast reaction. It creates NO+ and atomic nitrogen. So this is why the E region is mostly NO+ and not N2+. N2+ is created, but immediately becomes NO+. And then, of course, here are our recombination reactions. O2+ actually recombines with electron and splits, dissociative recombination. NO+ similarly, dissociative recombination. And atomic oxygen does the thing that we talked about before, where it gets an electron, actually becomes this metastable oxygen ion, oxygen atom, which metastable means it's a neutral atom, but it doesn't like that state. So after some amount of time, it'll decay back to a ground state and release a photon. And that is where we get our air glow, our 630 nanometers and 577.7 nanometer emission lines. Okay? So again, here's those profiles. You can see our O2+ and NO+ in the E region, and mostly O+ in the F region. So I'm not going to go through all of these. In fact, I will definitely skip these. But we can walk through, for the different altitudes, what are the dominant, these reactions I gave you here are kind of general everywhere. In different altitudes, different reactions are going to be more dominant dependent on the species. And the loss term is going to be a little bit different. So just for the E region, we'll just do it for the E region. The primary loss mechanism is, in fact, this recombination of O2+, this dissociative recombination. And so the loss term depends on that reaction rate and the density of these two species. So here's your loss term. And if O2+ is kind of almost equal to the electron density, and actually the NO+ reaction is comparable, so we can make that assumption reasonably well, then this is still kind of true, and therefore the equations I derived earlier are still kind of true. So the E region is a pretty good Chapman layer ionosphere. The F region is Chapman in some areas, in the sort of the F1 region, but not so much in the F2 region. And so this curve here from the top upwards is a very bad fit to a Chapman profile. And it's because of various other things going on. The vertical transport, electrostatic forces, there's a lot of other stuff happening in that part of the ionosphere. And then the D region is the worst of all. It's not even close to being a Chapman layer. Because the D region that I study has the same production mechanisms, but then there's all sorts of attachment processes that create negative ions, detachment again, and so you get some really actually weird profiles of the electron density as well as positive and negative ions. So that's those blue curves here, positive and negative ions, and then electrons. Ignore the red one. So D region's a little bit of a mess. This is the simplified D region chemistry model, which is in the Wacom model now, in Wacom X, so you can still run it. And it's largely because of these cluster ions that get formed. So there's water in the lower part of the atmosphere, H2O, and it attaches with protons pretty easily. And so there's 1 trillion different molecules of H2O, H+, and something else in here, and all these different reactions make it very complicated. So we'll get into the details there. Okay, the ionosphere's got temperature profiles as well. They're not the same as the neutral temperatures. The ions and electrons get their own temperatures. And so this is from the MSIS model, and there's some weird things in here that I won't read too much into because, again, it's coming from an empirical model. But if the black line there is my normal neutral temperature, red is electrons, blue is electrons, red is ions. This just highlights the deviation between these. The electrons, everything is kind of thermalized together in the bottom part, in the D region and lower E region. And then the electrons kind of separate, and then later on the ions separate. In this part of the atmosphere, they're still kind of collisionally tied to the neutrals, so they have the same temperature. But at higher altitudes, they become kind of independent. There you go. So the other piece that I haven't really talked about, again, in the ionosphere, we looked at everything kind of static, zero-dimensional, production and loss locally. But that equation I showed you, that it was dN dt is equal to production minus loss. I mentioned that's actually the continuity equation. If we add back in the other normal term that's in the continuity equation, which is the motion of particles, this is now the more accurate description. So everything from winds that move these ions to electric and magnetic fields to pressure gradients, etc., are going to move things around significantly. So I'm not going to get into too much of the details, obviously for time now. But just to highlight a few things, the neutral winds we talked about before, they actually will drag ions along with them, as I said. There's that ion drag term. So that's moving the ions around as well. That's going to happen in the parts of the atmosphere where the collision frequencies are high enough. But we also get things called drifts, and drifts are different from winds. This is where you have forces like electric and magnetic fields, gravity and pressure and so forth, which push particles around. So ultimately it becomes a very complex picture. All right, I'm going to skip over some of this stuff. Well, very quickly, just like the atmosphere, there's a big solar cycle variation, which should be no surprise because it's driven by the extreme ultraviolet and X-ray from the sun. So this is actually just measuring the peak density and the altitude. Isn't that? No, that's the solar flux. This is just the peak density in the ionosphere and correlating it with solar flux F10.7. And so you see that they track each other very well. Not perfectly, but pretty well. Okay, so that was very basic stuff, right? There's a lot more to this system, and if we had a lot more hours, you could dive into a lot of these different phenomena. I thought I would try to talk about a couple of interesting ones, and in the interest of time, I'll have to make it even just the fewest interesting ones. From the large scale here, there's a lot of phenomena that come from the lower atmosphere, or that come from the magnetosphere, or the solar wind, or you name it, that are driving this entire system. Whether it's what we've talked about with gravity waves and tides. I do want to talk about the equatorial anomaly in a second and some of the effects of the magnetic field. And in the polar regions, things are very interesting because of those relatively vertical magnetic field lines, open field lines. So there's direct access to the atmosphere of energy from the solar wind. And because of the magnetic field structure, we get all sorts of interesting stuff happening. Okay, so the things that I wanted to talk about, I created a list of interesting things to discuss here. We can talk about the E region dynamo, the F region dynamo, and the equatorial anomaly, TIDs, and radio wave absorption. I'm going to pick two. I'm going to do the equatorial anomaly, yeah, good, and radio wave absorption because that's my favorite topic. The equatorial anomaly, so we'll do number 2 here, is tied to the magnetic field. This is why I added this stuff in here. You guys have not had this lecture yet, right? Have you? No? Dungy cycle? A little bit? Okay. So you're looking at, this is a model from the Sigonenko magnetic field model, and it's showing you a little bit showing you the Dungy cycle. Solar wind magnetic field lines, reconnection, field lines wrapping around, propagating downwards, reconnections just off the page, field lines coming back in. And in this process, of course, the field lines are the out of the page part. This took me a long time to understand. The 2D slice is what you always see. The out of the page part is hard. These field lines are convecting over the poles. So 1, 2, 3 is all the way here in the tail. And then as the field lines move back in, they actually they split and go east and west, and they close in these little loops in the atmosphere on both sides. So that's creating this convection pattern on the top of Earth's atmosphere, which is going to drive a lot of the interesting effects. That doesn't actually tie to the equatorial anomaly at all. But we'll see the magnetic field anyway. All right, so I'll skip the E region. I do need this, though. So the E region dynamo I put in there in order to show how we get the equatorial electrojet. But we'll just start from the equatorial electrojet. So there is a current flowing along the magnetic equator in a relatively thin ribbon, 20 kilometers of altitude. So that's the E region, or the bottom of the thermosphere if you want. And it's flowing in this direction. It's flowing eastward. The overall current density is a fraction of an amp per meter, but there's a lot of meters. So if you integrate that, you get something like 100 kiloamps of current flowing around the Earth. It's not that high. It sounds high, but it's over a huge area. And so that current, because there's also a conductivity in the ionosphere atmosphere, there's an electric field associated with that as well. J is equal to sigma E. So here's magnetic field lines near the equator. So I'm looking, the equator's here. And that's the North Pole is up there, and the South Pole is down there in this picture. And the magnetic field lines in that equatorial region look kind of like so. And at the equator, the magnetic field lines are horizontal. And so there's a current and an electric field pointing into the page perpendicular to the magnetic field. All right, so here's that same picture again. I just described it. Yes, we're looking at this part of the Earth. There's the magnetic field. So now I've take that picture and flip it on its side to get this picture. And this is how the anomaly is produced. So the current is flowing into the page here, eastward, in this region, in the E region. And there's an electric field associated with that. So that's this electric field shown here. The magnetic field is horizontal. When I talked about drifts earlier, typical drifts are calculated, these drift velocities are calculated with, when there's some force on these particles, on charged particles with charge Q, in the presence of a magnetic field, you get a drift velocity that looks like this. And it's due to the Lorentz force. You can derive this directly from the Lorentz force. So F cross B divided by QB squared. If the force is an electric field, then I can plug that in, and I have this drift velocity, E cross B over B squared. So this is called E cross B drift, aptly. And there it is shown there. So if I have an electric field into the page, do right-hand rule, and a magnetic field this way, then I have a drift velocity upwards, away from the Earth in the vertical direction. So the ions in this region and electrons, notice the charge canceled out, so both electrons and ions drift in the same direction. They will drift upwards to higher altitudes. Eventually, they'll reach a region where the electric field is diminished, and so the drift kind of goes away. And then ions in this region, there's very low collision frequency. They really like to follow magnetic field lines, so they will fall back down along magnetic field lines in both directions to this region, north and south of the equator, where we end up with enhanced plasma density. So that's what's called the equatorial anomaly. And I found this was produced for the ICON mission, this little cartoon kind of showing that. The white arrows are supposed to be showing you neutral winds, which has to do with the generation of this current. And the blue is that electrojet current and the electric field associated with it. Purple are the magnetic field lines, and then green is that E cross B drift velocity. So it creates plasma enhancement here, which then falls back down on the field lines. This is one of the things the ICON mission was investigating. And so it's also referred to as the fountain effect because things go up and then they come down, back down the sides. And this is a nice simulation of that in a nice, pretty 3D sense where the Earth is rotating, so you're seeing the plasma density come around with the sun. This is mostly on the sun side because the electrojet current exists on the day side, And so we've got these two ribbons of enhanced plasma density off the magnetic equator. So this is one example, I guess, and since I don't have time to do more of them, there's a lot of really interesting examples where the combination of electric fields that are produced in the ionosphere and atmosphere for a variety of reasons interact with Earth's magnetic field to give us these E cross B drift motions and move the plasma around in unintuitive ways, I would say, and give us all sorts of interesting structures like this. This is the equatorial anomaly. The polar region gets even more interesting, definitely. So I'll skip over TIDs as other interesting phenomena. I was going to talk a little bit about the high latitude current systems. So like I said, the high latitude gets pretty weird because you've got currents flowing opposite to each other in different regions from the magnetosphere, these region 1 and region 2 currents. You've got electrojet currents in the ionosphere, and then of course there's electric fields associated with all of those things. And all of these different currents tie to currents in the magnetosphere, like this very weird. It's the substorm wedge current and the cross-tail current in black at the back there. These magnetosphere, magnetopause currents. So all this current system all connects back to the atmosphere, producing all sorts of weird things. Okay, I'll skip over this. All right, the last topic I'll talk about is radio wave propagation and absorption. So the very basic radio waves in a plasma phenomena. The first thing you'll learn about is the plasma frequency. If you have an electron density, Ne, and it's got charge, these three are constants, right? Mass of electron, charge of electron, permittivity of free space. Omega p is the plasma frequency associated with that plasma density. And it's the natural frequency that the plasma oscillates. If I were to, the picture that's often shown if you take this in an introductory lecture, is if I've got ions and electrons, if I could just drag all the electrons over here, it produces an electric field. And so they want to come back. But they will overshoot, and then they'll oscillate. And that natural oscillation frequency is omega p. So we use radio waves to communicate as well as to probe the ionosphere. And the plasma frequency sort of sets a cutoff for propagation through and within the ionosphere, within a plasma. Radio waves with a frequency above the plasma frequency, the plasma can't respond fast enough, so radio waves will propagate right through. It's essentially transparent to higher frequencies. So in this picture, there's a few rays here that are going right through the ionosphere. That one is unperturbed, so that's a high frequency wave. Radio waves below the plasma frequency, relatively slow oscillating electric and magnetic fields, they will cause the plasma to oscillate, and it'll essentially re-radiate, and that looks like a reflection. So waves at lower frequencies will reach the plasma where it reaches that plasma frequency, and they will reflect off the ionosphere. Although in actual fact, what's happening is it's re-radiating. So this tells us for practical purposes, obviously if we're communicating with satellites or we're doing GPS and stuff like that, we have to use high frequencies. But we can actually take advantage of this to do over-the-horizon communications at lower frequencies. So the medium frequency to lower HF range is commonly used for over-the-horizon communications or radar, taking advantage of reflection off the ionosphere. All right, so what are these frequencies? If you take the electron density in the E region and F region, just plug it into that equation. It's really simple. The typical cutoff frequencies are in the single digits to tens of megahertz, low tens of megahertz in the F region. So that's that minimum frequency. So it's not that hard, actually, to communicate with satellites. You need anything above like 100 megahertz. And we mostly use gigahertz. In the E region, it'll be lower, although occasionally there's a phenomenon called sporadic E that'll increase that up to 100 megahertz. In the D region, this simple model doesn't work because of collisions. Collision frequency in the D region changes the radio wave propagation characteristics, and it's just a little more complicated. But so anyway, waves generally reflect from the D region below about 100 kilohertz. And so really long-distance communications around the globe are used in the Earth ionosphere waveguide with the D region at VLF frequencies, because they will propagate and reflect all the way around the globe with very low attenuation. This is the Appleton-Hartree equation. This sort of defines the index of refraction in any plasma. This is just for electrons, but you can add in ions. It's got a plasma frequency in there, which is X. It's got a magnetic field in there, which is Y. Where's Y? There it is, and there. And it's got collisions through Z. And collisions make it complex. Everywhere you see Z, you see IZ. And that makes it, the index of refraction being complex means there's an imaginary component to it. The imaginary component of an index of refraction means absorption. Radio wave absorption, decay. So that's that right there. There's also the medium, magnetized plasma is anisotropic. So theta means that the index of refraction depends on direction relative to the magnetic field. And I won't get into too much of those details. So in the D region, This is very important because this high collision frequency leads to absorption of radio waves. And so I'll go back a second. Again, high collisions here, Z leads to an absorption component. This, the equation is written in terms of n squared, 1 minus this whole big mess, just because that's kind of the neatest way we can do it. You can solve for n. Analytically, I'm not sure you can actually solve for n, but you can approximately solve for n and get the real and imaginary components. And if you get the imaginary component, it looks something like this. And this is just a product of some constants, but electron density, electron neutral collision frequency, radio wave frequency, and the magnetic field, gyro frequency. So this tells me that if I have high number of electrons and a high electron neutral collision frequency, which really just means a lot of neutrals, the product of a lot of electrons and a lot of neutrals leads to absorption, that imaginary component of the index of refraction. So my electron density profile kind of looks like this, the blue curve. My neutral density profile, the atmosphere, which is basically proportional to the electron collision frequency, looks like that. If I take the product of those, I get a peak. And that peak is around between 90 and 105 kilometers. So that little region there, the top of the D region, the bottom of the E region, is where radio wave absorption occurs. And this was, obviously, it's frequency dependent. So I've done this for, I can't remember what frequency I used to calculate this, but in the megahertz range, HF, because we're mostly interested in HF communications. So these are just some profiles of collision frequency and some profiles of electron density during a geomagnetic storm, and showing us the change in absorption. This is differential absorption. You then integrate an altitude to get the total absorption in decibels due to this geomagnetic storm. So we went from the black curve here to these colored curves. And the black curve is way back here, not very much absorption, to then a lot of absorption. So things like geomagnetic storms or solar flares can do this as well, can actually cause a huge amount of absorption in the D region and block radio waves. You don't really block them, but they're absorbing them, so you can't communicate anymore. I don't need to talk about the collision frequency. This just shows, well, fine. This just shows that the collision frequency between electrons in N2, electrons in O2, is proportional to the number density and kind of depends a little bit on temperature, but not very strongly. So what I said earlier, mostly just the neutral density. So this will lead to things like a sudden ionospheric disturbance is actually the ionosphere response to a solar flare. In this very cartoony picture, the flare comes in, these X-rays ionize the atmosphere a little bit further. They actually create a significant additional ionization. And as I said, that the neutral density is not changing. Electron density just went up by a factor of 10, so my absorption goes up by a factor of 10. And that can lead to phenomena like this. So this thing is called a shortwave fade. This is the last thing that I'll go through. In radio wave communications, there is a lowest usable frequency, the LUF, which is set by absorption. There's always some absorption, and a lower frequency, the frequency is in the denominator, leads to higher absorption. I can't make the frequency much, much lower because absorption gets higher. So that sets my minimum frequency. And then there's a maximum frequency, which is really simple. That's just the reflection, the critical frequency in the ionosphere. If I use a frequency above that, it's just going through the ionosphere. So this is particularly, again, we're trying to use over the horizon radio. We're trying to reflect. So there's a maximum. During this type of event, during a big solar flare, the density can be so high that the absorption, the minimum usable frequency, is actually higher than the maximum usable frequency, in which case there's no communication. Right? So that's the simple picture there of how we get radio dropouts, blackouts. They call it a radio blackout. NOAA has a website that predicts radio blackouts based on X-ray flux measured on GOES. And so they're directly just looking at the X-rays. They have a kind of a quasi-analytical model to estimate the absorption. and predict when we're going to get radio blackouts. All right, so I will stop there because I was going to talk a little bit about WACM, but you'll probably hear more about that later on. And so here's just a quick summary of the stuff I talked about, and I will stop there.
So let's take 5 minutes for questions.
Yeah.
Yep.
Where's the box?
Hello. Yeah. So, are there any effects observed for SIDs in upper layers than D layers, like E and F layers?
Not really, and there's 2 reasons for that. Not really one reason, it's the same reason. Most of the absorption, so these SIDs are largely due to solar flares. So if I go back to the absorption, one of the various absorption plots that I showed you, cartoonish absorption plot, where are you? Came up a couple times. Back far. It has to do with where the radiation is absorbed. This little guy down here, which was also earlier, where'd my laser pointer go? This guy here. This is not a great picture. Actually, this is a better picture of it over here. Here's my ultraviolet radiation, right? So this is ionizing the thermosphere and producing the F region of the ionosphere. At that altitude, the collision frequency, the neutral density is very low. And so the collision frequency is very low. If you plug that into the equation, you get very little absorption. Even if we increase the electron density by an order of magnitude, the collision frequency is still way too low. It's that exponential decay with altitude. X-rays, solar flares, X-rays are down here. This would be better on a log scale in wavelength, but this tiny little sliver over here is X-rays. X-rays are absorbed in this altitude range. So that's why a solar flare has a huge impact on absorption, because of the altitude where the energy is absorbed. Geomagnetic storms will do it too, because when they cause electron precipitation is happening all the way down here as well. This is where the aurora is largely deposited, and higher energy particles go even lower in altitude.
So we can see SIDs in cases of solar flares and geomagnetic storms as well, right?
Yeah. The terminology SIDs it was developed with respect to flares, but you can have the same phenomenon, radio blackout, due to particle precipitation, geomagnetic storms. They don't tend to call them SIDs. Yeah.
I got a couple of more questions. Can I?
See if others have questions. There's a few.
We're actually way behind time, so I'm going to have 2 more questions. And Bob has contact information on his web.
Yes.
Okay.
So I have a question. How do
And our other local expert is for Zion.
how do neutral winds modify the electron density profile? Do they redistribute it horizontally or vertically?
How do they change the electron density profile? Neutral winds.
Yes.
That's getting a little bit out of my expertise. I don't know if Farzad has more on this. They're not going to change the electron density, but they can move the plasma around,
Yes,
right?
the movement of the plasma.
Yep.
Yes.
And actually, one of the interesting phenomena is, especially when you have a neutral horizontal wind, if you're in an altitude range where the ions are magnetized, then the neutrals will drag the ions, but the ions want to follow the magnetic field lines. And if you have a wind shear, they'll move them together. And that was, I don't know if it's still the theory, but for sporadic E, part of the theory is that the plasma is getting squeezed by wind shears. So that'll increase the density simply by moving plasma up and down. That's one example. I'm sure there are many others that are outside of my expertise.
We'll go with that one example. Well,
There's a couple.
I got time for one more question. We'll go here.
So you talked about E cross B drift, right?
Yeah.
So I was just wondering, like up to how much height the plasma will go? Like I was thinking like up to when the E and B will be perpendicular to each other. Like because as we go high enough, the curvature of the magnetic field increases, right?
The curvature of the field increases. That's not a huge factor,
So
definitely.
what's the
but
factor like up to
I don't know if I have it
what
here.
height it might go and then diffuse through?
Yeah, but so remember, the equation for the drift velocity is E cross B divided by B squared. The E and B magnitudes matter. The B is not really changing. You're changing in altitude a couple hundred kilometers, small difference. But so what really matters is where is the electric field sustained. And it's sustained generally at the lower altitude. So it'll drift until it leaves the electric field region, and that's where there's no more drift velocity, right? At that point, so the reason for the drift velocity is you're getting these little spirals of electron motion, right? And once the electric field is gone, the spirals just become circles. So at some point, at that point, then they're just going to follow the field lines back down, yeah. The exact altitude, I'm not sure. It's kind of in the F region. No exact altitude, of course. All right. Thank you.
So let's take a short issue.